area between the curves. And today, everything's going to be as a function of x, but we will also have to look at this as a function of y as well. On this first slide that we have here, I have a red function here, which is my f of x, and a blue function, which is my g of x. If I am trying to find, let's use a highlighter, the area that is between these two curves. So if I want the area of this weird shape right here, what would I have to do? Any ideas? Okay, so area under the red one would be, I would integrate, right? On this picture, that'd be from 1 to 5, because those are my limits here. And I would integrate f of x dx. What would that find? Oh, it'd find the whole thing. So that would find, I'm going to still use yellow right here. That would find all of this, right? That would find this area right here. And then I can integrate the blue one, which is g of x, and subtract. So that integral from 1 to 5 of g of x would find this area right here. And if I subtract the two, then that gives me the area in between those two curves, right? I could write my integral like I've written it, or because I have the same limits and the same variable, I could also write it like this, the integral from 1 to 5 of f of x minus g of x dx. And a lot of times we'll find, like in practice, it's easier to put those two together whenever you integrate. Okay, does that make sense? If you understand the integral as being the area under the curve, to me it's pretty easy to arrive at this idea of, to find the area in between, you just have to subtract those two there. So you'll see these problems both in calculator inactive and calculator active. So when we're doing calculator inactive problems, like example 1, the big thing is you have to know what the graphs of these functions look like. Because if you don't know what the graphs of the functions look like, it's going to be hard to decide which one is your top function and which one is your bottom function whenever you're looking at this. So whenever you get something like example 1 here, it says find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x, x equals 0, and x equals 1. We need to pretty much graph all of these. So y equals x squared plus 2. What does that look like? Parabola up 2. So it's going to have a y-intercept right here. If I plug in 1 squared plus 2 is 3. That'll be here. If I plug in 2 squared plus 3 is 6. It's going to go off of the graph here. So we're going to have like something like this right here. And then I've got y equals negative x. What does that look like? It's linear, right? It's got a slope of negative 1. Negative 1 doesn't look quite as negative as even here because of the scale on this graph, but it'll look like this. Then I've got x equals 0. What is x equals 0? Vertical line at 0 right here. And last I've got x equals 1. That's going to be another vertical line right there. Okay, so what we're looking for here is this area right here that's enclosed by all four of those graphs. Now, this one might seem a little bit different because up here we were doing this area minus this area. If you kind of think about what's going to happen here, if switch here, if I integrate my blue graph, what would my limits need to be? 0 to 1 of x squared plus 2 dx. If I integrate that, that is this area right here. Right, that, oh gosh, it looks green, but that would be this area. Whenever I integrate the red function, if I integrate from 0 to 1 of negative x dx, that would be, let's see if the pink will show different, yeah. That'd be this area right here. Now, it looks like those should be added together rather than subtracted, right? But this second one, this red area here, the value of that, is it going to be positive or negative? I'm going to get a negative. So if I put subtraction right here in between, I'm going to be subtracting a negative, which will be like adding, right? So for these problems, you are always doing top equation minus the bottom. Even if it like goes below the x-axis, that minus, that negative part will just take care of it where it looks like it's adding it together. Now, I would suggest on this, to make it a little bit easier to evaluate, I would put these together. So your interval is the same, and it should be. I would do x squared plus 2, and you're doing minus negative x here, which of course is going to become a positive right there. So we are integrating, I would write it this way, x squared plus x plus 2 dx. Okay, questions so far? All right, once you get to this is just a definite integral problem that you've got to work out. You're going to have x to the third. You will divide out front by that 3 and get a 1/3. Over here you'll get x squared. You'll have a 1/2 out front, and then you'll get a plus 2x, and we will evaluate that from 0 to 1. And so we've got to plug in 1 and 0 and subtract. So I've got 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1 minus 1/3 times 0 cubed plus 1/2 times 0 squared plus 2 times 0. And so this is going to be 1/3 plus 1/2 plus 2. What are we going to get over here for that last part? Just 0, because you're multiplying everything by 0. So it's really just 1/3 plus 1/2 plus 2. You need to get common denominators for this, so you'll multiply this by 2 and get 2 over 6. You'll multiply this one by 3 and get 3 over 6, and you'll multiply this one by 6 and get 12 over 6, and that will give you 15, 16, 17 over 6 as your area. Okay. You can see this definitely allows us to be able to find areas of shapes that we could not find areas of shapes before. This triangle would have been no problem. We could have done that part by hand, but this we would not have been able to do until we started integrating here. This also is going to be applicable whenever you have like a rate in, rate out problem as well, but we're mostly talking about the graphical analysis of this here. All right, so if we look at 2, this is still one that would be calculator active. Find the area bounded by the graphs of f of x equals 2 minus x squared. I don't know why that is an and instead of an equals right there. That should say equals. And g of x equals x. Now, this one, did they give us the interval that we're supposed to look at? They did not. So that tells me probably these two graphs cross somewhere. And if you kind of think about what you're looking at, this is a parabola upside down, moved up some, and then you've got y equals x is just a line like this. So we're probably looking at something that looks a little like this. We need to know where those cross, right, so that we can tell, and we need to know which function is on top and which one is on bottom. Because whenever you integrate, you always have to do the top minus the bottom. Also, should we ever get a negative answer for any of these problems? We should not. It is area. Area should always be positive. So if you end up with a negative answer, what probably happened is you put the wrong equation on top. You put the bottom on the top, and that messed it up. So there's a couple ways that you could do this particular problem. You could try to do a graph, or if I want to know where two graphs cross, what can I do with them algebraically? Somebody take a guess. Set them equal to each other. That's exactly right. So we can take 2 minus x squared and x and set them equal to each other. I would move everything to the right side. This is going to be a quadratic. So it will be x squared plus x minus 2 if we move everything over there to that right side. And I just chose the right, so I didn't have a negative x squared. That makes it hard to factor. And on the calculator inactive problem, you're going to have you will have something that will probably factor. So here we'd have x, and we could do it plus 2 minus 1. And so that would give us x equals negative 2 and x equals positive 1. So those are going to be our points of intersection here. So like the x coordinate where this intersects over here is negative 2 something, and over here we intersect at 1 something. Actually, g of x equals x, so it's going to be negative 2, and 1, 1 there, because they have to be on the line. G of x equals x. Y coordinate's not really that important. You don't necessarily have to find it. Now, I do need to know for sure that I've drawn this like f of x is my top function. And just based on what graphs look like, I think that's probably going to be correct. But I want to know for sure that f is my top function. So I could, again, try to graph it. This one's not terrible to graph. Or what else could I do to know which function is going to be on the top? You could do that. If you get a negative number, whenever you get the answer, just switch them, because you know that that's wrong. Another option here is if I pick any number between negative 2 and 1 and plug it into both of them. So the easiest number between negative 2 and 1 is just 0. So if I do f of 0, I would do 2 minus 0 squared. That would give me 2. So that means I've got the point 0, 2. So like that's going to be your maximum point, is right here on that graph. And then if I plug in g of 0, I just get 0. So I can tell if I plug in the same number that's on that interval into both functions, 2 is higher than 0. So that would be our top function there. Yes?
How would g of x be bigger, be the top graph if they have to intersect?
If like, for example, the parabola had been moved down, if it was like a -2 minus x squared, then what you'd be looking at would be, like, you'd have this, and the parabola would actually be, like, down here, which they would really have to give you, like, they'd have to give you some, like, vertical lines to make that work. So it just depends on the situation. I would feel fairly confident that this picture I have drawn up here is correct, even without plugging in some numbers here. But in some other situations, it might be harder to tell, so plugging in a number will let you know for sure which one is top and which one is bottom. Okay, so f is my top function, so I need to integrate from -2 to 1, because those are my intersection points. And I'm going to go ahead and put them together this time. I'm going to integrate from -2 to 1, and I'm going to do f of x, which is 2 minus x squared, minus g of x, which is just x, and then I'm going to put the dx over here on the end for that. And then I just like to clean that up a little bit before I actually integrate. So I would have, I like doing the highest exponent first. Negative x squared minus x plus 2 dx. Okay, so Lucian, whenever we integrate this, what will we get? We need to keep the negative with it. It'll be negative 1/3 x cubed. Good. Keep going. So what's your exponent right here? 1. There's not 1, so the exponent's 1. What do we got to do with the exponent? Increase it by 1. So you'll have x squared. Then what do you do with that exponent? We're going to divide out front, so we'll have 1/2. And then we'll keep that negative there with it. And then what will you get for the 2, Lucian? 2x, perfect. So we get plus 2x right there. And we are integrating this from -2 to 1. Everybody good here? Okay, so we need to plug in 1, we need to plug in -2, we need to subtract the 2 there, so we're going to have negative 1/3 times 1 cubed minus 1/2 times 1 squared plus 2 times 1. That's our first part, minus negative 1/3, negative 2 cubed minus 1/2 times -2 squared plus 2 times -2. And so that will give us negative 1/3 minus 1/2 plus 2. And then over here, what is -2 to the third? -8. And we'll multiply that by negative 1/2. We will get a positive 8/3. What is -2 squared? Positive 4. 1/2. Negative 1/2 times positive 4 is going to give us a -2. And then we'll get a -4 right here. And so this is going to give us negative 1/3 minus 1/2 plus 2 minus 8/3. That's going to be a -6, but then it's going to become a +6 when the negative gets distributed to it there. I would probably go ahead and put those thirds together, which if I have -1/3 minus 8/3, that gives me -9/3, which is -3. So I've got -3 minus 1/2 plus 2 plus 6. We put those two right there together. And if we put our whole numbers together, we are going to have 8. We're going to subtract 3. We get 5 minus 1/2. So 4.5 or 9/2 if you want to do it as a fraction. Now, lots of instances where we need to get all the way down to the actual answer, but sometimes you don't. So if it's a FRQ, make sure your parentheses are right, and you can stop right here for that. Now, if you need to use the answer for anything, you're probably going to need to keep that a little bit longer. If you have multiple choice, obviously they're not going to leave the answer like that either. Okay, questions? I would like for you on these when you get to the homework to try to do the simplification without a calculator because that practice will make you more proficient with it. Sometimes our textbook gets a little carried away and gives you stuff a little bigger than this, but something like this they very well may ask you on the exam where you do need to be able to do all that calculation without a calculator. Good here. All right, so let's look at this one. This one is asking us to sketch a graph of the region whose area can be found by evaluating this function. So, why is it doing weird things? Where I click, asking you to actually evaluate. They're asking you just a graph like this, and I'll give you some graph paper if you need it for those. There. So sometimes you need to be able to see a picture and know what to evaluate from that picture. Sometimes you don't have the picture at all and you've got to come up with it so you can do the problem. Sometimes they give you the equation and ask you to match that to the correct picture. There. All right. Okay, the sine and cosine curves intersect at infinitely many places. Find the area of one of the regions bounded by f of x equals sine x and g of x equals cosine x. So now is a wonderful time for us to review the graphs of sine and cosine. So, what is the highest sine ever goes and the lowest sine ever goes? 1 and -1, right? So -1 is the lowest we need to go. +1 is the highest we need to go. And remember, the sine and cosine graphs are connected to the unit circle, right? So the really key points whenever you're graphing sine and cosine are 0, pi over 2, pi, 3 pi over 2, and then back over here, 0 is the same as 2 pi, right? So, if I graph those 4, I could graph others in between, but these 4 will get you a pretty good graph. This would be 2 pi here, pi over 2 pi, 3 pi over 2. And then I could do the same over here if I wanted. Oh wait, -pi over 2, -pi, -3 pi over 2. Okay, so let's think first about f of x equals sine x. What is sine of 0? Sine of 0 right here, the coordinates of this point are 1, 0. Sine is your y coordinate. So sine of 0 is 0. Its y-intercept is right here on the x at the origin. Okay. What is sine of pi over 2? It is 1 because this is the point 0, 1. It's your y coordinate. Right. From here, you probably can remember the pattern for these, but it comes from the unit circle. So if you forget, this point right here is negative 1, 0. So you're back to 0. This point right here is 0, negative 1. So your sine is negative 1. And then you go back to 0 again. And same pattern over here on the left side. And we can kind of draw in our curves. I made that too low. The graph's not perfect here. Actually. Okay. Everybody kind of remember that graph that we've seen a lot of times. Then let's use red for our cosine graph. What is cosine of 0? It is 1. So now you're looking at your y-coordinates. And you should remember you go from maximum to the midline, minimum, back to the midline, back up to the maximum. That same pattern over here on this side. And so if we draw in that graph, and it would be better if my graph was graphed perfectly, but sine and cosine intersect at infinite places. So we could be looking at maybe this section, or we could be looking at this section, or we could be looking at this over here, although our graph doesn't quite go far enough there. We could be looking at this one right here. We could do any of these. It doesn't matter which one you choose to do. I would suggest that we look at this one right here because all of our x values are positive right here. It'll be a little bit easier to think about on the unit circle. They are, if I had drawn it a little better, they're all the same size. Mine's not perfect here. This one looks a little small, but that's because I graphed it a little bit out of proportion. But all of these are going to be the same size here. So we can find one, then that's the area of one of those regions. Question though. In order to do this, we need to know the top function, bottom function, and our limits that we need to use. So let's do I think top function, bottom function is easier. What's the top function? Sine. So we're doing sine of x. What's bottom? Cosine. So sine of x minus cosine of x. That's what we're integrating. Okay? Now, question for you. These intersection points, where are they? What are the limits? Pi over 4 is our lower one. Perfect. No. 5 pi over 4. Because these will be the places on the unit circle where we have the same value. So right here at pi over 4, you got square root of 2 over 2 and square root of 2 over 2. Those sine and cosine are equal there. And that same thing happens over here in the third quadrant at 5 pi over 4. You got negative square root of 2 over 2 and negative square root of 2 over 2. There. Everybody get there? All right, we must integrate this. What is the integral of sine? Negative cosine. What's the integral of cosine? It's positive sine, but there is already a minus there in the problem, so you'll end up with a minus sine x. And we will evaluate this from pi over 4 to 5 pi over 4. So we will have negative cosine of 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine of pi over 4 minus sine of pi over 4. What is cosine of 5 pi over 4? Negative square root of 2 over 2. So we're going to have negative square root of 2 over 2 minus another negative square root of 2 over 2, because sine and cosine are equal to each other at that point, minus negative, what is cosine of pi over 4? Square root of 2 over 2 minus, this is also going to give us the square root of 2 over 2. So you got to keep all your signs straight here. These double negatives right here are going to become positive. And then you are going to distribute this negative to these over here, which is going to make everything positive, right? We're basically just adding the square root of 2 over 2 four times, which is the same as multiplication, right? That's repeated multiplication. So you could write this as 4 times the square root of 2 over 2. No, said that backwards. Multiplication is repeated addition. So this is 4 times square root of 2 over 2. That's like 4 over 1. That 4 can cancel with that 2 right there, and you will get 2 square root of 2 as your answer. Hello? Yes. You're welcome. Reagan, I need you in the office. Okay. All right, questions. Like if I had 2 plus 2 plus 2 plus 2, to use a much easier number, I could write that as 4 times 2. So since I'm adding square root of 2 over 2 plus square root of 2 over 2 plus square root of 2 over 2 plus square root of 2 over 2 four times, I can just write it as 4 times the square root of 2 over 2. Yeah. Yeah. Okay. Other questions? All right, so your assignment comes from your book. Let me double check that this is right, because sometimes I don't update this like I want it. All right, we haven't had our books out in a while. All right. All right. 1 through 4 is not asking you to solve. It's only asking you to set up the integral. So 1 through 4, you don't have to solve. It's only asking you to set up the integral. You'll end up doing too much work if you solve those. It'll take you a lot longer. So 1 through 4, just set it up. 7 and 8 is asking you to sketch a graph. I'll give everybody a piece of graph paper if you need it to help you on that. But 7 and 8 are sketching graphs. So again, you're not solving that on 7 and 8. You are just sketching the graph. Then 19 through 25 is where you'll actually be solving those out for those. Okay. Questions? All right, I'll give everybody a piece of graph paper too. And you got plenty of time to work.